Hello students, this is Dr. Ben, and I'd like to take a few minutes to work out a problem out of Chapter 5 of our textbook that has to do with the topic of uniform circular motion, and it's actually about the kinematics of that uniform circular motion. So we've got this scenario presented where we're looking at the Milky Way galaxy, and one of the stars that is in the galaxy, which is our Sun. We're given some information about the rotation of the Milky Way galaxy. So I'll go ahead and make a table of what I know for this problem. We know the period of the motion that we're talking about is 200 million years, so that would be equal to 200 times 10 to the 6th years. And I may need to convert that into seconds later on in the problem. And then the object of interest is the Sun that is rotating around the center of the Milky Way galaxy, and we're given that its radius is 2 times 10 to the 20th meters. Alright, and so what we want to find in this problem is given in the second paragraph, and so that's some information about the motion of the Sun, and we're asked to find out how fast it's moving with respect to the center, and so that would be equal to the speed that I could write as v, or I could write it as the magnitude of the velocity. Alright, so let's draw a little sketch of this uniform circular motion. And so let's pretend that we're looking at this situation from the top. And so that circle represents the orbit of the Sun about the center of the Milky Way galaxy. And at a particular point in time, the Sun might be located at that point that I drew on the right hand side of this diagram, and there would be its velocity v, and we know that the properties of uniform circular motion are that velocity is tangent to the circle, and so it makes a 90-degree angle with the radius. Alright, so the circle of the Sun's orbit has a radius that's given by r, and the rotation rate, well, the Sun is rotating around the center, and the period of that rotation is the symbol t. Alright, so we need to go onto our formula sheet and find the appropriate equations for the kinematics of uniform circular motion. And so basically we would want to start with the equation that the linear velocity v is equal to the angular velocity omega multiplied by the radius r, and we can write the angular velocity in terms of the period because it would be equal to 2 pi divided by the period. So the angular velocity would be the angular displacement divided by the time elapsed, and so that would be for one revolution, and we multiply that by the radius then. Alright, so it's not clear what system of units we should use, so maybe we'll just keep the units that are in the problem, and we'll record the speed of the Sun in meters per year. We could convert that to meters per second if we wanted to. So numerically, we're going to take the value 2 pi and we'll divide it by the period, 200 times 10 to the 6 years, and then that's going to get multiplied by the radius, which is 2 times 10 to the 20 meters. So I'll get my calculator out and do that arithmetic. 2 times pi divided by 200 million times 2 times 10 to the 20th, so that equals 6.28 times 10 to the 12, and that would have the units of meters per year. So we could convert that speed to some other system of units if we wanted to. We could change it to meters per second or kilometers per year or something like that. But that is a reasonable correct units for speed, and we just use the natural units that were given in the problem. Alright, so I have my units specified, kind of odd, but they're reasonable, and my significant figures might have one too many, but 3 looks to be okay. Alright, so there we have the speed of the sun about the center of the Milky Way galaxy.